Hello, welcome to this first video on concepts from formal verification and formal control. So there's a book that I'll be using to kind of help out with these videos. It's called Verification and Control of Hybrid Systems by Paulo Tabuada. And this is a really impactful book within the field, and for anyone who's interested, I'm going to be using the notation from the book, so feel free to look into it in more detail yourself if you're interested. So the definition of a system that we're going to give in this series is that a system is a mathematical model of a dynamical phenomenon. And there's several different types of system. So you can have a finite state system. So this is a system which, as you might have guessed, can be described with a finite number of states. For example, finite state machines in computer science. You can have infinite state systems. So these we would often describe with difference equations or differential equations, and their solutions evolve in an infinite set, such as the set of real values. And then you also have hybrid systems, and these combine aspects of infinite state systems and finite state systems. But first of all, I'm going to give the definition for a system which is used in this book. So we have the system S, we have a set of states X, we have a set of initial states X0, we have a set of inputs U, we have a transition, a relation, which we're going to denote with an arrow. We have a set of outputs. And then finally, we have some sort of output map, which maps from our states to our outputs. So it's a sextuplet. So as I said, we've got a set of states. Inside this set of states, we'll have individual states. So I'll use lowercase x for individual states, and these all belong to the set of states X. We have a set of initial states, X0. So this could be a subset of X. It could be a proper subset of X. These states could also equal X. The whole state space could be the initial set of states. But it could also equal just a single state as well. We have a set of inputs, and again we can denote one element of the set of inputs with a lowercase u, and then we've got the set of inputs u. We have this transition relation denoted by the arrow, and so this will be some subset of a state, as well as any input, as well as the state that it transitions to. So for example, we could have the state transition from X0, which goes to the state X1 via some input U0, and we can denote this as a tuple. So we'd have this, and as you can see, this is a subset of the set of states, because X0 is an element of the set X, U0 is an element of the set U, and X1 is an element of the set X as well. And so this set composition here would define the whole set that can hold all the transitions. We have a set of outputs. So again, we could have a single output, which is in the set of outputs Y, and we have a mapping H. And so this mapping H maps from the set of states to the set of outputs. And so this here is the simple system definition that we're going to use. So a few things to say on this. So these states X are considered to be internal to the system, while the outputs Y are generally externally visible to, for example, other systems or to the user. If X is a finite set of states, then the system is finite. Otherwise, if X isn't finite, then the whole system is an infinite state system. As I've already mentioned, the initial states could be a proper subset, and they could equal the whole set of states, or they could be a single state. And we use finite and infinite when we're talking and quantifying the state space that this system belongs in. But if we want to quantify how it evolves over time, we would describe a discrete time system or a continuous time system. So a discrete time system has like jumps, which are all of a similar interval. And then we also have continuous time systems, and this would consider the continuous behavior of the system. And so we would represent continuous time systems using differential equations. So the evolution of the system we've talked about a little bit already is represented by the transition relation. So here, the transition x with the input u to a new state x dash can be written as well as x transitioning with input u to x dash. So these two things are basically equivalent. And so this state here, x dash, we can consider this to be called a u successor state, or even just a successor state, to be simpler. And then x here, with regard to x dash, could be a u predecessor state, or just a predecessor state. Another thing is that because this transition belongs to this set here, we know then also that x could have multiple inputs that it can use, and it could have multiple successors. So from that perspective, we could have a set of successor states as well. And so we denote the set of successor states from some initial state x under some input u, using this here. So we would say post of subscript u of x, and so this would be the set of successor states. The set of successor states could also be empty. So this would be if you choose some input u for a state x and there is no successor state x dash. So in this case, if we want to denote whether, if we want to know which inputs provide us with successor states, then we also have another function, u of x, and we use u of x to denote any inputs which, when applied to x, will have successor states. And so this is where post of x would be non-empty. So I'll use not equal. Okay, because I'm aware this video is very long. So we now have here, we have our sets. So we have a set of states, x0, x1, x2, x3. We've got our initial set, which is x0 and x2. We have our input set, which is u0 and u1. And we have a transition relation with 6 different transitions here. We have an output set with 3 outputs. And then we have our mapping. So we have the mapping from the state inside the brackets to some output. So x0 to y0, x1 to y0, x2 to y1, and x3 to y2. And one of the great things about systems is that we can describe these using a graphical form. So I'm just going to draw 4 circles here, representing each of these states, x0, x1, x2, and x3. And we denote using a bar the outputs of each of these. So here x0 goes to y0, x1 also goes to y0, x3 goes to y2, x2 goes to y1, and then we can mark on the transitions with the inputs. So x0 goes to x1 using input u0, and I'll just finish this off by myself, and then I'll rejoin you. Okay, so now I have the rest of these transitions marked in. So we have the transition using u0 here, u0, this is like a self loop, u0 from x1 to x3, and then we have the transitions u1, so from x0 to x2, x3 to x1, and x2 to x3. We've also got this initial states here, and so we mark these using an arrow which doesn't come from any state. So x0 was one of them, and also x2. So these are the 2 initial states. And this graphical representation is really helpful for us to see what's happening with the system. So this is a finite state system, and we can see we have our finite states and we have our transitions, and we have this nice graphical representation of how it works. Okay, so now let's discuss a few of the properties of these systems. So the first one is determinism. So for determinism, what we have is that for any state x belonging to the set of states and any input u belonging to the set of inputs, then we could have 2 transitions, so x under u going to x dash, and also x under u going to x dash dash. And here, if we can imply that x dash equals x dash dash, then the system is deterministic. So what we're saying here is that for every state and every input, there should only be one successor state, or maximum one successor state. There could be 0, but there should only be one successor state which that maps to. And so in this case, if x dash and x dash dash, they would have to be the same if the system is deterministic. They'd have to be the same state. For non-determinism, then what we would have is that it would be possible for one state under the same input to have potentially different successor states. So I could write this like this. Non-determinism, it would be possible for us to have 2 transitions using the same input where x dash and x dash dash are not the same state. Another property we have is output determinism. And what we mean by output determinism is that the outputs from the system, so we can write this like h of x dash, because we're considered the same here, and we could have the other one is h of x dash dash. So if there's output determinism, then if these 2 outputs are equal to one another, we can infer then that x dash equals x dash dash. So if a system is output deterministic, then it should be possible for us to differentiate between different states using the outputs, because every state will only have one output associated with it. So for different outputs, if the outputs are the same, then it shouldn't be possible it should be possible for us to know which states they came from. So in summary, for output determinism, different successors of states should always have different outputs. Otherwise, you have output non-determinism. Another property we have is blocking. So if a system is blocking, then there should exist some state within our set where U of X is the empty set. And what that means is that there should be some state within the system where there is no input which gives us a successor state. So in essence, when you reach that state, the system is now blocked because you can't transition anywhere else. There's no transitions that follow from that state. So therefore, a non-blocking system should have it be the case. So therefore, a non-blocking system should say, for all the states in the system, then this function U of X is not the empty set. So what we're saying here is that every single state should have some transition, so the system is never trapped, it's never blocked anywhere. So finally, let's look at then again at our graphical representation. So what we can see is that this system is non-deterministic. So take x1 here, we have the transition u0 which goes to x1, and we also have the transition u0 which goes from x1 to x3. So in this case we have non-determinism because we have here x1, let's write it, and this goes to x1 under u0, and then we also have x1 going under u0 but going to x3. And as x1 does not equal x3, then we know that this system is non-deterministic. However, this system is output deterministic. So there's no states here when they're a successor state that have equal outputs. So you might be thinking, but what about here? We've got x0 has the output y0 and x1 has the output y0. They're the same, so how does that work? Well, there is no state which can transition to both x0 and x1. So therefore, actually, these two, the system is still output deterministic because there's no case where x0 and x1 are both successor states. And so, feel free to look for yourself at this, or if you can get access to the book, have a look at the example in figure 1.1 there. But this system is output deterministic. I'm about to leave it there for today's video, but it's useful to think about how we can simplify this system definition. So if I'll write it again, so we have S equals X, the set of states, X0, the set of initial states, U, the set of inputs, an arrow representing the transition relation, Y representing the outputs, and H, which is the map from state to output. If the set of initial states is equal to the set of states, we can just simplify this, and we can have S equals X, U, the transition relation, Y, and H. If our outputs Y are just equivalent to the set of states, and if H is the identity matrix, so we're going to write the identity matrix like this, then we can also simplify the system. So now we can say that we have the set of states, we have the initial states, we have U, and we have the transition relation, and we know that Y equals X, and so the transition relation will be from X to X, and so then we also don't need this mapping. And then finally, we can make an even more simplifications, where if we say that the initial state is the whole set of states, that the outputs are equal to the set of states, and that the mapping is the identity matrix, well then now we can reduce this all the way down to just a simple tuple. So depending on your state, your system, you might want to describe it in different ways. And so these are just some ways to try and help with that. But I'm sure this is a very long first video. I hope to get better and better at this as I do more of them. But thank you very much for listening, and I really appreciate your attention.